We'll get started here in just a minute. We've got 12 people in right now, so let's see if we get a couple of stragglers here. What you can see in front of you are the results from exam 1. So I hope you can read that okay. 4 A's, 3 B's, 2 C's, 3 D's, 8 not passing. And then the little dots on the right show the actual grades of each student. I had 20 students take the exam. All right, so in terms of this exam, I mean, normally exam 1 is a pretty decent exam in terms of students' performance. I'm a little bit surprised by the results. Class average 66.3, standard deviation of 22 points, meaning that there's a really big spread of where the grades lie. When you have a small standard deviation, it kind of means like the whole class is together. You're either all doing okay together, or you're all not doing okay together, but at least you're all together. With a standard deviation of 22, that means we've got like 2 ends of the spectrum here. And that's always very difficult as an instructor to try and teach to a class that has that separation. But you know, it's the first exam. We still have a few more, all right? We have, what, 3 more? And so there's plenty of time to improve your grade. Unfortunately, though, the material, you know, exam 2 material, I think, well, I don't know. We'll see how it goes, all right? I mean, it is what it is. This class actually did better than my other class. My other class average was a 60 and the standard deviation of 27, which is huge. I mean, normally a good standard deviation or an average standard deviation is around 14. So anything over 14, you get into like 16, 17, that's where you've got this big spread of students. 27 is just massive. So, but I think that's because these 2 grades here were just so far out there that that really skewed the data. Any comments on the exam? I've sent it back to you. You should have been able to access it. You should have been able to access the graded exam, like a copy of your exam with my markings on it. So that should be in the Canvas gradebook. As far as the exam is concerned, this is the exam. What I went and did was kind of wrote down next to each problem, like where that problem, the idea behind that problem came from. So the first 2, those were just like derivatives using chain rule, product rule, and formulas off your formula sheet. So I think the first 2 were just, you know, differentiation. Okay, so Cal 1 stuff. And then number 2, there were 2 problems like this on page 252, number 29, number 30. The third one, I remember warning you all about this problem. I said, I like to give this on a test. And students do all sorts of crazy things instead of just splitting it up into 4 separate integrals and just using the power rule on each one. Number 4 was very similar to number 25 out of 5.5 substitution. Number 5 was like number 26, except I think it was sine here instead of secant squared. Number 6 I did in class, or something like it in class. Let me see. This would have been substitution. Man, I don't know if I'm able to find. There's something like it. Anyway, okay, so let's see. Okay, number 7 was like a problem that we did in class where you had to realize this was x cubed squared. This was like number 34. Actually, this was number 34 out of the homework problems. This was exactly number 34. And then number 9 was very much like number 4 out of 6.1. This is integration by parts. And then number 10 was very much like number 10 and number 19 out of 6.1. And then the bonus, well, the bonus was the bonus. So I don't want to go through the whole exam and show all the answers and go through how each problem was worked out. If you want to do that, feel free to come, join me in office hours, or we can set up a special Zoom meeting. I'd be happy to go through your exam with you and kind of talk you through where the mistakes were. Because normally on the exam, I'll mark out like where there's a mistake, or I'll just put like -6 or something. And so each problem is worth 10. So if I do -6, that means that maybe there was maybe you were using substitution, but there was something way off. If I did -3, then that means, you took it pretty far, but there were some errors. So if you have a question on why I took off what I did, just set up a meeting with me and we can go through it.
Can you go over question 3 from the test?
I can talk about it right there. Yeah. That's it right there.
Oh.
You're supposed to split it up into 3 integrals.
Okay.
Convert these using exponent properties, and then just use power rule, and on this one, that's a natural log.
So this one was very simple. I thought that it was like U substitution, or if not even U substitution, I thought this was like integrals, like integration with parts. So yeah. That's why I didn't get it further.
Yeah, no, you weren't alone. You weren't alone. There are quite a few people that made that problem much more difficult than it had to be. And if you're ever taking a test, and when I'm grading tests, sometimes I wonder this. If you ever find yourself like going down roads that you've never gone down, like doing stuff that you've never done, that's usually an indication that something is wrong. Like, I'm not going to throw a problem. I would never throw a problem like this at you if it were like integration by parts, because I've never given you anything like that, and you've never had a homework problem like that. So anytime you start to feel like, wait a minute, this is looking really bad, then you might want to just take a step back and rethink it.
Sir, are you allowed to send this file to us?
I'm allowed to. Yes, I am allowed to. Do you want me to?
Yeah, could you send this to me?
Yeah, I can just send it to everyone.
Oh, yeah, thank you.
No, I'll just send it right now. Oops. Solutions fall 20. Okay, so let me throw that in the chat. I'm just gonna put it in the chat. You should be able to get it there.
Thank you.
If I can find it. I don't remember where I just put that. Oh, there we go. There, it's in the chat. Okay, so we move on, right? That's our only real, that's one thing that's guaranteed about this class is that the train will continue to move. So if you didn't do well, okay, like what's the next step, right? If you didn't do well, you can't get too down about it, but the alarm bells must go off. Like, you have to do something different. You have to try a different way of studying, a different way of approaching the way you're doing homework. You need to come to my office hours, and not my office hours the day of the exam, right before the exam. I'm talking like consistently come to my office hours. I'm more than happy during my office hours to just throw problems at you and let you try and work things and talk through what you're thinking. But you've got to make an adjustment on your end. Right now I have maybe, I can count on one hand how many students have come to me during office hours. I've had 5 people visit, but it's the same 2 people that have come 5 times. And they're not even in this class, they're in a different class. So take advantage of that. And if you cannot meet me during my office hours, just send me a text message saying, hey, are you available? I'm at home now with Zoom, just like you are. And so if I'm not busy, I don't mind jumping on the computer real quick. It's not a big deal. If I'm free, I'm happy to help you, you know? So, but you've got to reach out. I'm not gonna email you and say, hey, let's do some calculus right now. You know, it's gotta be you. All right. Let's get down to business. So we are not done with integration by parts. We still have 2 more examples that I want to show you. And this is the first one, all right? So this is an integration by parts problem because I just said it was, right? And I think you saw that on the test. That's part of the challenge, right? Is knowing what to do with the integral. Like, what method is it? So this one is an integration by parts, but it's really kind of tricky. Let's see. Let's try and set up our table where we pick U and then dV. Oh, hey, I'm going to mention one more thing. I was talking to one of my colleagues yesterday, and we were talking about the calculus sequence and how it's difficult in Zoom to do things like classwork and group activities. But we both agree that like true learning happens when you work together in groups. Like when you're able to talk through things with other people, explain things to other people, that really solidifies what you know, right? So again, I can't force you to do this, but I would highly encourage you to take advantage of the fact that you have Zoom and you can meet with your classmates. Y'all can set up study groups. You can do that, you know. I will help facilitate that if you want me to. I can even, if you talk to a few of your classmates through email and y'all decide, hey, here's a day and a time, you know, then I'd be willing to open up a Zoom session for y'all to join, or one of you can set up the Zoom session. I'll help, whatever it takes. But I encourage you to try and work together, you know, with your classmates. I think that would really help, especially for those of you who struggled on that first exam. All right. Okay, so here's my integration by parts, U, dV. I only have one choice for you, right? I only have one choice. Because there's really only 2 things being multiplied here, e to the square root of x and dx, that's it. So dv has to be dx, and then u has to be e to the root x, right? That's it, that's my only choice. So I'm gonna just see what happens here. So I'm gonna differentiate down. The derivative of e to the root x is itself, times the derivative of the square root of x, you can't forget that, right? And then dx. And then you have to do the other one, you have to integrate. So you integrate 1, and the antiderivative of 1 with respect to x is x. And this doesn't look very nice, but we can still do it. We can still at least set up the ultraviolet minus the integral of voodoo. So that should become ultraviolet, which is going to be x times e to the root x, minus the integral. I'll leave a little space here in case I have any constants. Do I have any constants that come out? I'm looking at voodoo right now.
1/2.
1/2, so I can pull a half out. And then let me just kind of put everything else there. I'll just write it all down first. Okay, that's what I have. Now, when you simplify this, this right here can just turn into the square root of x, right? E to the, x over the square root of x is just the square root of x. I'll write it this way. All right, did we get any better here? Did things get better or not? I mean, we started with just e to the root x, and our new integral is root x e to the root x, right?
I think it's going to cancel the roots.
How do you mean?
No, I think that was some other property. I thought maybe the under root in front of the e and the power could cancel out.
Yeah, there's nothing that's going to save us there.
So we'll have to take another,
We could try integration by parts again, right? We could try it. It might get more complicated, right? So at this point, you should be thinking, all right, so what should be going through your mind is, why am I a STEM major? No, I'm kidding, right? No, this is where you're like, okay, this one's going to be tough. I've got to somehow figure this out, right? Here's the challenge. So I'm showing you this example because this is a good example of how if you do something at the beginning of the problem that doesn't even seem like you should, it's going to make the problem easier. All right. So we're gonna restart the problem, but right here you're thinking, what the hell? This didn't get better; it got worse. Okay, so I'm going to start the problem over. And I realize what I'm about to do is just, you're probably going to sit there and be like, you know, like, I don't know if I would have thought to do that. I'm going to make a basic substitution. So I'm not doing integration by parts. I'm just making a basic substitution. I'm going to replace u with the square root of x. Now, when we were learning basic substitution, I said that when you do basic substitution, you should be looking for something and its derivative, right? Something and its derivative. So here I've got my something. There it is, root x. I can replace that with u, but I don't see its derivative anywhere. Do you? No, right? The derivative of the square root of x is 1 over 2 root x. I don't see that anywhere, but it's still going to work. All right. That sucks, doesn't it? I mean, doesn't that suck that this is going to work even though it doesn't look like it's going to work? I mean, that should bother you a little bit.
I mean, it does, because that's the whole basis of U substitution, because if it's not going to look like that, then you would have to do that. That's my theory of looking at integration by parts. For question 9 and 10 on the test, I tried thinking to do U substitution, but then I realized that there's no way I could get,
Yeah, so what I'm trying to get at here is that I understand the challenge here when you're learning this, is that you're looking for like almost like a pattern. You're looking for something that you can see it and latch onto it and be like, okay, when I see that, I'm going to do this. But you just have to be willing to continue to pull out different things and try something else, and this is going to work. Okay, so dx, there's dx. Now I have all this other crap in front of dx, right? Like I've got 1 over 2 root x, and I'm like, I don't know what to do with that, right? Like the 1/2, I can just multiply both sides by 2 and I'd be happy, right? It would go away. But it's that root x that's a problem. But does anyone see what I can replace root x with? What is root x? It's u, isn't it? Isn't it u? Okay, so watch. I'm going to do something real quick. I'm going to multiply both sides of this equation, this one, by 2 root x, right? And it'll go away on the right-hand side, right? If I multiply both sides by 2 root x, it vanishes on the right, and on the left-hand side, 2 root x appears. And now I'm going to use the fact that u is the square root of x, and I'm going to stick it right there. So this becomes 2u du equals dx. And now do you see that we will be able to replace everything in the integral with something that has u in it? You'll see that?
Yes.
This will become integral. Let's see. Oh, I do have a 2, right? I have a 2 that can come out. I'm going to have a u, I'm going to have an e to the u, and I'm going to have du. Does everyone understand where all those pieces came from?
Yes.
Yes? Okay. Now, you look at that. Look at that problem. And let's look at exam 1. This is basically that problem right there, except with u's, isn't it? So now we're ready for an integration by parts. So getting the problem to this point, right? Let me scrap all this. we started here. We did a basic substitution first, a basic U sub. When we did the basic U sub, we now have this new integral. And to do that integral, I'm going to use integration by parts. Make sense? Okay, now I have to be a little careful now. You have to be a little careful now because the integration by parts formula is ultraviolet minus integral voodoo. I can't use that formula the way it's written because I've already made a substitution of U. So I'm already using U for something else. So I'm gonna have to change this formula to be a different letter. Like maybe I'll do W and then DW. Do y'all see what I'm saying? Like I can't use U in two different places to mean two different things. So instead of putting U here, I'm gonna put W here. And over here, I'm gonna put, wait a minute, hold on. Yeah, and then here, this is gonna be DV.
So is it like compulsory? Because I think it's just to make sure that you don't get confused.
That's right.
Yeah.
Yep. Yep. Okay, so now let's do the integration by parts. We are going to replace W with what? So which of these two pieces are going to be our W?
EU.
So e to the u, if we do that, then in the new integral, what would our voodoo? You need to think about what voodoo is going to be. What's
1 over 2 by U squared.
okay, that's what will be in the top right hand corner. That would be V.
Mm-hmm.
And if we let W be the e to the u, the derivative of that would be e to the u, right?
E to the U with 1 over U?
Yeah,
No.
with 1 over 2u squared. But that's more complicated than the original expression.
Yes.
So why don't we put u here and e to the u here? Do it that way.
Oh, yes. Yeah,
And then
yeah.
when we
That
differentiate the u, it becomes a 1. It'll be a better integral. So this will become 1 du, and this v will become e to the u. So now we have 2 integral, oh wait, sorry, no integral, 2, and now the formula. So we're going to multiply these two together. When we multiply those two together, we get u e to the u minus the integral of the voodoo, which is the diagonal part here. And that's just e to the u du. And the antiderivative of e to the u du is just e to the u again. So we have 2 u e to the u minus e to the u plus some constant. And we're almost there. We're going to distribute the 2 through, and then we're going to replace all of our u's with what? What was u?
Square root of x.
under root x.
Root x, okay? So we're going to go back now. We're going to distribute the 2 through 2 root x, e to the root x minus 2e to the root x plus c. So this example, again, was to illustrate how you may try something in the beginning, integration by parts, you realize that that gives you something more complicated, so then you go back and you do a substitution that doesn't even seem like it's going to work, but it actually gives you a new integral that you can do by integration by parts. So you do integration by parts, but you have to change the variable because you've already used u, so you use a different letter, and then it works out.
And I have a question
Yes.
regarding both the U substitution and integration by parts. So is there a way, can we solve questions for U substitution by doing integration by parts?
Usually not. Usually it's one or the other. Now, this is an example where you needed u sub first, and then you did integration by parts. I think what you're asking is, are there problems where you could do it either way? Like u sub would get you to the answer, or integration by parts would get. In general, no. In general, like it's usually going to be one method works and the other doesn't?
Because they're so similar in nature that it's hard to distinguish.
Yeah. Yeah. I agree. All right, the next example that we're going to look at actually comes from something I wanted to show you first.
I had a question.
What do you got?
So could you scroll up on that current page
Oh.
here?
All the way?
Yeah. So I can't just take do the substitution by parts here again, where you're.
Integration by parts here again.
Yeah.
I don't think it'll work. What would you use for your U? And then du.
Okay. Yeah.
So if you let the U be the root x, right?
Yeah.
Well, if you do that, you're going to go back to where you came from.
Mm-hmm.
Because, well, you'll have a problem here at this part right there. When you're trying to go up here, you see that?
Mm-hmm.
You're trying to go up, that's the original problem. And you don't know the answer to that, right? So if you switch it around and you don't do it that way, you do it this way, you put the e to the root x here, and you put the root x here, now this derivative is going to give you 1 over 2 root x e to the root x, and then the antiderivative of that's going to give you 2/3 x to the 3/2. And you put all that together and you're going to wind up getting 1/3. I'm just looking at the integral you're going to get, the voodoo.
Mm-hmm.
You're going to get 1/3 x e to the root x dx. And now again, you're still not, you're not at this position that we were here. This was u e to the u. This is x e to the root x. So it's not the same as what we had just a second ago. So this is still more complicated than the original expression.
Okay.
Yeah, so I think we're kind of jammed up right here. All right, so your formula sheets, right? You have these formula sheets, and on your formula sheets, I gave you, all these reference pages, right? And it stops at reference page 6. That's where it stops. And it's a good 29 formulas. And we haven't looked at all these. I mean, we've looked at the first few, but these are all formulas that help you find antiderivatives without you having to do any work. You just use the formula. But if you were to actually have the physical textbook in your hands right now, you would see that there's a bunch of formulas in the book. So I'm going to flip back here to the page we stop at. So the last page I gave you was reference page 6, and it stops with formula 29. But there's another reference page 7. There's reference page 8. There's reference page 9, right? And I've seen like textbooks, thick textbooks that have nothing but integral formulas in them. And they were, these reference pages, these formulas were made by mathematicians and that basically were trying to make tables for people that needed to do integrals before computers came along. Like now you can do integrals, just go to Wolfram Alpha or some other software and you can just, website, you can go get an antiderivative, no problem. But before that, we had these tables that we would have to reference. So if you were an engineer and you need to do some weird integral and you'd come here like, oh, there it is. Oh yeah, there's the formula. I don't need to actually remember how to do any of the math. Here's the formula. So I could pick any of these formulas, but there's one in particular that I'd like to do, and that's this formula 73. So that's what I'm going to look at. I have it here. Here's formula 73. And I want us to look at the formula first, and then let's discuss what the formula does. And then what we're going to do is we're going to see where the formula came from. We're actually going to make the formula. And this formula is called a reduction formula. And the reason it's called a reduction formula, I should go back and take spelling. Reduction formula is that what happens is it says, this says if you have an integral where you have sine raised to the n, okay? So maybe it's sine to the 3rd power, sine to the 5th power, sine to the 100th power. And you want to find the antiderivative, you just follow this formula. So let's just pick an arbitrary value in here. Let's say it was 8, okay? Then the answer would be -1/8 sine of 7, because I'm subtracting 1 from n. Do y'all see that, right? N minus 1. U cosine u plus, okay, n minus 1 is 7/8, so 7/8 integral sine to the what power? Where am I at? N minus 2? 6. 6th power u du. Make sense? Now, we don't have the answer. This is not the answer because we still have an integral to do, don't we? We have to figure out what that integral is. But do you see what's happened to the power? We started out with 8, now where are we? The power's been reduced, right, to 6. So guess what? We get to just reuse the formula again. So everything in blue here, I can imagine that everything in blue here is in brackets, okay? And now let's just figure out what that is according to the formula. According to the formula, again, it would be -1 over what? So I'm just using this again with a different n, right? 6 sine of 5, or sine to the 5th u cosine u plus
5/6.
6 integral sine to the 4th u du, right? All of that is the blue part. But we still have an integral, don't we? We have this integral, sine to the 4th. But guess what we get to do again? Use the formula again, right? And so I could say everything in brackets here gets replaced with, and then I run through the formula again, it'll take it down to sine squared, right? And then I have to do it again to take it from sine squared down to sine to the 0. Sine to the 0 is 1. So this formula allows me to take sine raised to any power and just keep on chipping away at it with the formula until I get down to an integral I can do. So I'm reducing the power each time I use the formula, and that's why it's called a reduction formula. Does that make sense?
So when you get to your answer at the end, is it going to be like an incredibly long answer?
Well, it's gonna, yeah, oh yeah, it's gonna be really nasty.
Okay.
It's gonna be really nasty because remember, you have, your answer is gonna be this, right? And then all of that gets replaced by all of this, but then all of that would be replaced by something else. And there was another integral in there that would have had to have been reduced again, which will be something else. So it's like you have to plug all those things back in. So yeah, it'd be terrible. It'd be terrible, but you know, that's what it would be. Where's Wolfram alpha?
So is it going to be till the part where we have no more power left?
Yep. Or until that integral that's at the end is something you can handle. Like it might be sine, like let's say we started out with a power of 9. First time we get 7, second time 5, third time we get 3, right? The last time we need it, we would get down to sine to the 1st power. And you know the antiderivative of sine is negative cosine. So then you'd be okay. So I'm gonna go to Wolfram alpha real quick, and I'm gonna say integrate sine of x, all of that raised to the 8th power. Now, the answer may not be that long because, yeah, see, they use a bunch of trig identities. Yeah, so it doesn't look as bad as it actually is because they used a bunch of trig identities to make it simple. Okay. You know, and while I'm here, I might mention this to you. In the real world, right, an engineer is not going to compute an integral by hand. An engineer is going to go to a computer, and the computer is going to do the work because the computer is not going to make the mistake, right? It's not going to miss the sign. It's not. So you might be sitting here going, well, then why are we learning this, right? And I think that's a very valid question. So I have two kind of answers for that. Number one, I hope that you would all agree that this is a higher level of thinking in this class than, let's say, calculus or pre-cal or college algebra, right? It's not mechanical math. And I told you this in the very beginning. This is different, right? It's a different type of problem solving. It's a different type of critical thinking. So it's to develop that in you, number one. And number two is more of you have to remember something about taking math courses. A lot of people take math courses because they feel like, because they want to be an engineer or computer science major, and this is part of the requirements, right? So you have to do it. So a lot of people are looking at it as, you know, how does this apply to what I want to do? Well, it's kind of like we all had to take English, right? Like we all have to take an English class, a government class, right? And I have to present this material as if you were all math majors. Like someone in this group could potentially switch over to math, right? And become a math major. And in that respect, the value of us being able to do this by hand is that, how can I make this make more sense? Okay, so when I was a math student, I had a project when I was an undergraduate student. I had a project my senior year in a class called numerical analysis. I almost forgot the name of the class. And our project was that we had to take a computer program that's used by engineers or mathematicians, or, you know, Wolfram or MATLAB, or, you know, all these different programs. And what we had to do is, whatever the program was, we had to basically feed that program a problem, okay? And the problem that we were gonna feed the program, we had to understand that problem. We had to be able to find its solution. So we needed to know its solution theoretically. So we had to be able to show what the answer was to the problem without a computer. And then we needed to send this problem through the program and get an answer. And our job, our task, was to see if we could get the computer to give us a wrong answer. In other words, we had to understand how the program was written. And we had to exploit the weaknesses within the program. So maybe within the program, there was some rounding errors. So we would feed it a problem that would exploit the rounding errors and make it give us something wrong. And so the value of something like this is, for an engineer, you're going to use a program. Trust me, you're going to use a program to solve problems for you. But this is what we call the black box. The engineer has no idea the math behind that, right? What math took place to get to that answer. So how can you trust that answer? You're going to trust it, right? You're going to go build a bridge with it. You're going to go build an aircraft with it, right? So who knows the program? Who knows whether or not that math is right? Who knows? The mathematician knows, right? The mathematician knows what the weaknesses of that program are. So if we start teaching calculus, where every time we have an integral, we just go to a computer, at some point you lose people who actually know the mathematics. Does that make sense? It's very dangerous. So I have to present this material to you as if you are a math major and not just turn to the computer to get all our answers. We have to still stick to the theory. I hope that makes sense. Okay. So this formula, where the hell did it go? Where'd it go? I know I had it here. Oh, there, okay. So what we're gonna do right now is we are going to see if we can prove the formula. You all ready for this? We're going to prove that this is true. So we don't, this in red, we don't know this, okay? We're starting with this integral and we're gonna generate that formula. Okay, so here's how I'm gonna do it. Now, look, you will only see a problem like this appear on a test as a bonus question. All right, that's the only way it's ever going to appear. I'm never going to test you on this, but you should see the journey of this because I think it's valuable. So the first step to this.
Oh, question.
Yes.
Can I write this on the back of one of my formula sheets, reference sheets?
Yeah, I don't mind if you have this one.
Okay.
Yeah, I mean, as you saw though, there's a bunch of others, right?
Yeah.
Okay.
I know you don't want us to have the textbook out during tests.
Yeah. So here we go. First thing I'm going to do is I'm going to rewrite this sine to the n minus 1u times sine u du. So I'm rewriting the original integral. And what I'm doing is I'm rewriting sine to the n as two things being multiplied. So it's kind of like this. If I was writing sine to the 6th u, I'm rewriting as sine to the 5th u times sine u. So I'm basically just peeling off one factor of sine. Is that okay? Do y'all agree that that's a legal move for me to do that? Yeah? Okay, the next step, let me see if I can remember the next step. Yeah, yeah. Hold on, I'm like second guessing myself. The next step is I'm going to do integration by parts. I'm going to pick a u and I'm going to pick a dv. Now, this choice is going to come from the fact that I peeled that sine u du off. I peeled that off, didn't I? And I did that so that my dv could be sine. So I'm going to make this my sine u du. And I like that because the antiderivative of that would just be cosine of u. And, sorry, negative cosine of u. Are you all right with that? Okay, now that forces my u to be everything that was left. So it's sine to the n minus 1 of u. And now I need to differentiate that. So if you're sitting there wondering what's the derivative of sine to the n minus 1 of u, just ask yourself this. What would be the derivative of sine to the 5th of u? Just chain rule, right? Power comes out first. So what's going to come out for us?
N minus 1?
N minus 1. And then I will reduce the power by 1. So now it's sine to the n minus 2 of u. Chain rule times. So think about this. This would be 5
U
times to the 4th u times the derivative of the sine, which would be cosine u. Right? So we still have a cosine u here, du.
And aren't we supposed to take the derivative of u as well?
Yes, which is the du.
Okay.
The du at the end is the derivative of u.
Okay.
All right, so that's it. Now I'm just going to set up my integration by parts. All right, we have ultraviolet, these two things multiplied, so I'm going to write that down. That means this is going to become, do it this way. This is going to become equal to negative sine to the n minus 1 of u cosine u. Everyone see that's just the yellow part multiplied together? Okay. Minus a little bit of a space in front, integral. Okay, any constants that can come out. N minus 1 is a constant, right? Negative 1 in front of the cosine is a constant. So I can change that in the front there to be a plus, and then in parentheses n minus 1. Is that all right? Constants came out. Now, the part that's still in the integral is sine to the n minus 2 of u. And then I have cosine times cosine, right? Twice. So cosine squared u du. All right. Any questions? No?
Why is there a negative in front of sine? Or like, where did that come from?
We're here? This one?
Okay.
Is that what you're asking?
The the where it says negative sign to the n minus 1?
Oh, right here, that came from this negative because I multiplied these two together, right? So I just put that negative out in front.
Okay.
Now, is this the formula? Is this formula or no? Not really, right? I mean, it's kind of. We've got a sine to the n minus 1 u cosine u. I've got that here, but I don't have a negative 1 over n out front. Here I've got n minus 1 over n. I don't have that. I just have n minus 1. Then here I have sine to the n minus 2 of u du. Here I've got sine to the n minus 2 of u times cosine squared u du. So this, so far it's not, we're not there, right? We're not there? Okay, so the next step is I'm going to remind you from pre-cal what this is. Using the Pythagorean identity.
Professor,
Yes.
can you hear me?
Yes.
So the first integral that you see in there, written in red, the sine n minus 1 u du, where did we get that? Yes.
Yeah, so that is not, that's just.
That's something given?
No, it wasn't given. This is what was given. This
Okay.
is what I did. I split it into two, just like you would be able to split sine to the 6th into 2 pieces. I split it into 2 because it's going to work. And that's why I said this would be a bonus problem. This is not something that you would naturally do. But now that you've seen it, if you were faced with, like, let's say this was cosine to the n instead of sine, maybe you would split it into 2 and then set up integration by parts. That makes sense? So this is just kind of like, where did that come from? Well, because algebraically it's correct, right? I can do that.
Mm-hmm.
Yeah.
I see it now. Thanks.
Okay, so this part in yellow, cosine squared u. Going to go back to the good old Pythagorean identity. Sine squared u plus cosine squared u equals 1. Going to solve it for cosine squared u, so I'm going to subtract sine squared u on both sides. So I'm going to replace cosine squared u with 1 minus sine squared u. Let's do that. So this is equal to negative sine to the n minus 1 of u cosine u plus n minus 1 integral sine to the n minus 2 of u times 1 minus sine squared u du. So that's just replacing cosine squared with what it is from pre-cal. Now, why is this going to work? Well, let's distribute. So if I distribute, I'm going to get sine to the n minus 2 of u minus sine to what power?
Cube.
What do you do to those powers?
0.
You add them, right? N
You
minus
add
2 plus 2? What's n minus 2 plus 2?
Sine to
N.
the n.
Sine to the nu du. Yeah? I'm going to keep going. Watch what I do here. You have to be very careful with what I'm about to do. So just watch, and then we'll talk about the algebra here. Okay, do y'all see what I did? Took the constant in front of the integral, I distributed it through to both of those, and then I split it into 2 integrals. Yay or nay? Is that fair? I mean, is that algebraically okay?
Yes.
Yeah? Okay, now why the hell did I do that? Well, what's the original problem? What was the original integral we were trying to solve? Integral sine to the n u du, right? That's the original problem? Yeah?
Mm-hmm.
Isn't that what this integral is? It has appeared again on the right-hand side. How many of them do I have on the right-hand side? How many of these green integrals do I have? N minus 1, right? That's how many there are? Okay? And I'm subtracting that. Why don't we move that to the other side of the equation? So why don't I add to this n minus 1 integrals of sine to the nu du? And let's do that to this side. It will go away on the right side. And on the left side, how many of those integrals do you have? Be careful. How many of them are there? How many do you have right here? What's the coefficient out in front of that integral?
1.
1. Okay, so I have one of those, right? And then I'm going to add to it, how many of them?
N minus 1.
N minus 1. So what's 1 plus n minus 1? Just n, right? Just n. So I have n of these integrals.
Confusing.
If your head is spinning, like I get it, I understand. Okay, there's where we are. One more step. One more step. Divide everything by n. And so what we get is integral sine to the n u du equals, now this n down here, I'm just going to put it out in front as a negative 1 over n, sine to the n minus 1 u cosine u. And then this n minus 1 over n, I'm going to put it out front as a plus n minus 1 over n integral sine to the n minus 2 u du. And that is the formula. Right? That's the formula. So it's, you know, that formula, it looks like it's very complicated and like, where in the world would that come from? Well, that's where it came from, right there, right? These things are not just like, I mean, someone took a lot of their life to figure that out, okay? As you can see, there are very, very unnatural things that I did just now to make that happen. But all it took was integration by parts and keeping track of our algebra. That's it. That's all it required. Some careful choices of the way to split things up, everything works out. So these reduction formulas are very difficult to, you know, generally, it's very difficult to prove these formulas because it requires something special to make it happen. But each one of these comes from something. Right?
So, random question. What would happen if you didn't FOIL out the n minus 1? Which it would just wouldn't work, right?
If you did, at what point?
Right here with that yellow, where you FOILed that out, that n minus 1.
Yeah, if you didn't do that, then you'd be trying to do the antiderivative of this, and you'd be stuck because that's the original problem.
Mm-hmm.
And then this one, you still don't know what. Well, that's part of your answer. So I mean, the fact that it appeared here is making you feel good because you know that the formula had it in there, but this piece wasn't there. So you just kind of, I don't know what you would do there. You'd just be stuck, I guess. You have to see that the original integral appears on the right-hand side. You have to see that, oh, wow, that's the thing I was looking for, and I'll move it over. That's happened to us one other time. That happened to us right here on this problem. I put 3 stars by this when we did this on the 10th. So this is one of those problems where you do integration by parts and you don't think it's going to work, and then all of a sudden the thing you're looking for appears again on the right hand side. You're like, oh crap, I'm going to just add it to both sides. That's exactly what just happened, but it was just different because it had n in there instead of x's and stuff. All right.
I have a question.
Yep.
So are these considered equations that we would use, or are these considered properties?
These are considered formulas.
Okay.
Yeah. So this is just like you have the, you know, any equation. You could say it's an equation. Okay. It is an equation.
Mhm.
The left and right hand sides are equal. We
Professor,
use it
could you
as-
bring the screen a little lower just to finish the writing the problem?
Yeah, so all of those formulas, those integral formulas, are equations where we use them to make our lives easier when it comes to integration.
Okay.
Now, this was proving the formula. When I started this off, I showed you, like, had we started with like sine to the 8th power, you'd still have to use the reduction formula several times. And it wouldn't be fun, but I mean, you could do it. In theory, if you had sine to the 100th power, you could use this formula. You're just gonna have to chip it down by 2 each time. It's gonna take like 50 iterations of it.
50 iterations, oh my gosh.
Yeah. But it's a way to do it, right?
Right.
All right, that is it for 6.1. Okay, we are done with integration by parts in the sense that we're ready to move on. Integration by parts won't ever leave. It's always going to be here, but we are now ready to open up a new can of worms, and that is 6.2, all right? So remember in the beginning of the semester, I was talking to you about like what this class is about and you know how it's different. And do you feel as students sitting there, do you feel like this class is delivering on what I promised it would be? Like does it feel like I was trying to get you to understand that this is going to be different? Do you feel it? Do you feel like it is? No?
Yes.
Definitely.
Yeah. I think you're getting a sense for why people say this class is difficult. You know, because it's just nothing is freaking easy here. Everything requires a lot of thinking. All right, the first part of, okay, so 6.2, let me tell you what this section is about. We're still trying to figure out antiderivatives, okay? So we're still sitting there going, okay, there's other integrals out there that we still don't know how to do. That U substitution is not going to work and integration by parts isn't going to work. So this section deals with what are called, this section has two separate topics. One of them is called trig integrals, and those are trigonometric integrals. Those are integrals that involve sine, cosine, tangent, cosecant, secant, cotangent. The 6 basic trig functions from pre-cal. Any integral that has one of the 6 basic trig functions in it and nothing else, like no other algebra, like, so this would be a trig integral. Like, what is the antiderivative of cosine squared x dx? That's a trig integral. If you were to throw in front of that an x cosine squared x dx, this is no longer a trig integral because it involves something that's not trig in there, like x by itself, right? Or if I made that x squared, then that's no longer trig integral. Do you understand? Trig integrals involve one of the 6 trig functions in the integral or some combination of the 6 trig functions together with nothing else. Then the second half of this section is something called trigonometric substitutions. So all we're going to talk about for the next 40 minutes is the first part of this, and we're not going to finish it, I don't think. We're just going to talk about trig integrals. Once we figure out how to do trig integrals, once we get comfortable with that, Then we can move to the second part. You can't do the second part without the first step. You have to be good at trig integrals to do trig substitutions. That's why they're in the same section, because the second part depends on the first part. All right, so some stuff we already know. All right, so this is good news. This is stuff we should already know. Antiderivative sine, we know that. What's the antiderivative cosine? We know that, right? We also know that if you put a constant in front of there, like a linear expression, we know that we have to scale by 1 over a, right? We talked about that a while back. So that we know. So now what we want to do is develop a strategy for attacking integrals that involve various powers. What's going on here? Hold on a second. Why is that not working? Okay, hold on. Having a problem here. Pen, 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 no, pen. Try it one more time. If it doesn't work, yeah, I don't know why it's not working. Okay. Various powers of sine and cosine. So here's a strategy. And I'm not going to read through the strategy yet. Okay, what we're going to do is we're going to do a problem. And as we do the problem, we're going to read through the strategy. Because if I just read this all out to you, you'll be like, what the hell? The important thing to know, though, is that to use this strategy, there's a few formulas from pre-cal that we need to be familiar with. The first one is the Pythagorean identity, which everyone here should be comfortable with. Sine squared x plus cosine squared x equals 1, right? We all okay with that? There's two other formulas that we need to be familiar with, and these are called the half angle or power reducing formulas from pre-cal. And what it was a formula that allowed you to take sine squared and take the power off of it. And it becomes 1/2 1 minus cosine 2x. Or if you distribute the 1/2 through, you get this formula. You may have seen it. Well, let's look at it in the formula sheet. See if it looks familiar to you. This is back in pre-cal. Oh, here we go. Oh, you know what? I actually don't think this formula sheet, oh, it does have it. Here we go. Half angle formulas, here they are. Do those look familiar, pre-cal? Hmm?
Yeah, I think I remember them from pre-cal.
So the thing is, like in pre-cal, when you're learning these formulas, a lot of times you're taught how to do these things mechanically with these formulas, and you're never really told back in those courses like why you need to do this. And so when I teach pre-cal, I always tell my students, look, this half angle formula, you are going to need this big time in Cal 2. Like you're going to need it. You're going to have to be able to use it. So I'm here to remind you that it's there, and now we get to play with it. All right. Notice my version of the formulas are a little different. I pulled the 1/2 out. Here, the 2 is on the bottom, so imagine just pulling that 2 as a 1/2 out in front. It's the same formula, right? All right, let's get down to business then. We're going to use those formulas to go after some problems. So the first one we're going to do is the integral of sine cubed of 4t dt. Let's go ahead and just focus all of our attention on this. Basic U sub. Basic U sub, no, right? I don't see something in its derivative. Integration by parts. You could maybe let this whole thing be your U and let your du be dt or dv be dt. But this, now that we're talking about trig integrals, you should have a little light bulb that goes off, says, I see trig, I see nothing but trig. This is a trig integral. How do we do trig integrals? Here's how we do it.
Can we use reduction formula on this?
You could use the reduction formula on this. You could. The problem with that is that reduction formula is not on your formula sheet. Now, I just said to Cameron that you could write it down, but if this were like cosine cubed, you wouldn't have anything to go to, right?
Okay.
And you're not allowed to have all of those formulas. Okay, so what is the procedure here? What is the procedure? If we have a trig integral, well, let's read through it. If you have cosine to the n, with n being odd, do we have that? Do we have a cosine? We don't,
No.
right? So we're just going to skip one. Let's go to part 2. If you have sine to the n with n being odd, do we have that? Do we have sine raised to a power? That power is odd. Yes. Okay. So we're going to be doing 2 here. All right. So what does it say for us to do? Use the Pythagorean identity. So I'm going to use this identity right here. I'm going to write it down. I'm going to write my Pythagorean identity down over here. That sine squared x plus cosine squared x equals 1. Okay, I'm going to use that Pythagorean identity. And I'm really upset that my highlighter's not working. I don't know why. Let me quit this. Let me try reopening this program. Okay. Oh, I know why. There it is. Okay, so we have sine to an odd power. We got that. We're going to use a Pythagorean identity. And what we want to do is factor out a single sign. Okay, we want to look at the original expression and we want to factor out a single sign. So that means I'm going to go like this. Sine squared 4t times sine 4t dt. Do you see what I've done is I've taken the fact that I had 3 factors of sine and I've just written it as sine squared times sine. So I've factored out 1 factor.
Yes, I had a question regarding that. I was thinking if you could do that, and now can you try doing the U sub?
Yes, almost. Okay, so let's continue reading through this. We're going to factor out a single sign, which leaves an even power of sine. It's going to leave us an even power of sine. How do we know it will always leave us an even power of sine?
We always start with an odd.
Because in this particular step 2, we started with odd, right? So if we start with odd and we peel 1 sign off, whatever's left will be even, right? Okay.
Question.
Yes.
What if you started with like sine to the 5th? Would you pull it out twice?
Nope. You would just, if you had sine to the 5th, you would pull a sign out and you'd be left with sine to the 4th,
Mm-hmm.
which would be even, wouldn't it?
Yes.
Okay. So that's where we are in these steps. Factor out a single sign, which leaves us with an even power of sine. Now, what do we do with that even power of sine? We are now going to rewrite the remaining power of sine using the Pythagorean identity. So that means I'm going to rewrite this right here. I'm going to rewrite that using the Pythagorean identity. So think about your Pythagorean identity up here. If we solve that for sine squared x, we get 1 minus cosine squared x, don't we? Just move the cosine squared x to the other side. So I can rewrite this as 1 minus cosine squared what?
4t.
4t. Okay, that is this piece. And then I still have the rest of it. Sine 4t dt. So do y'all see what what we were able to do by doing that? Do y'all see what the next step is going to be?
What about the 1/2 in the formula?
I didn't use that formula. I used the Pythagorean identity. I did not use the half angle identity. You see the difference? Okay, so do y'all see what this got us to?
Yes.
This is a basic U substitution now. Do you see something in its derivative? Cosine, what's the derivative of cosine? Negative sine, do you have negative sine? You're off by a sign, but yes, you have sine out there, don't you?
Yes.
So you can make a substitution now that u is equal to cosine of 4t. The derivative of that is -4 sine 4t. Where'd that -4 come from? Chain rule there, right? Chain rule. So I will be able to replace cosine 4t with u. I will be able to replace sine 4t dt, sine 4t dt. I've got to scale this out. I've got to do a -1/4 on both sides. Please just interrupt me if you have a question. It's rewrite the integral time. Who wants to tell me what the new integral is going to be?
-1/4
-1/4.
integral 1 minus u times du.
Close. 1 minus u
Square.
squared. So don't forget that little squared on the cosine. Otherwise, that's perfect. Yeah? And do we know the antiderivative of that? I hope we do. U minus 1/3 u cubed plus c. So I'm just using power rule on that. Questions?
Where is the u coming from? Because I think it was 1 minus u squared.
I did put u squared. Oh, wait. I'm not sure what part you're talking about. Talking
So
about
The integral of 1. It's
The
u.
antiderivative of 1 is just u.
the antiderivative of 1 is u.
Oh, okay.
You good with that?
Understandable.
I know you know that. It just slipped out of your mind there for a moment. All right, now we just plug u back in. So -1/4, u is cosine of 4t, plus a 12th cosine cubed 4t plus c. So I did distribute the -1/4 through. And I replaced my u's with cosine 4t, and that's why I have that little cubed on there, right?
Mhm.
There it is. So if we have an integral that has sign in it, and that sign is to an odd power, we're going to peel off a sign. We're going to look at the even power of sign, use the Pythagorean identity to rewrite it in terms of cosine, and then we're going to make a substitution, u is equal to cosine. And then everything should work out.
I have a question.
Yes.
So in order to use this rule, the exponent has to be an odd number. It cannot be an even number, right? Okay.
That's right. Can't be even. Now,
So if you had, oh, go ahead.
if you have even, we do have a method.
Oh,
We just
okay.
haven't gotten to it yet.
Okay, got
So
it.
far, the only thing we can deal with is sine to an odd, right?
Mm-hmm.
But we're going to
And
want,
that
we are
means-
going to want to be able to do sine to an even. We're going to want to be able to do cosine to an odd and cosine to an even.
Okay,
Yeah.
got it.
So let's do another one. I don't know if I'm going to work through this whole problem, but what if we have sine to the 5th this time? Well, peel off, right? Sine is to an odd. Let's peel off one factor of sine. Now, here's where we have to rewrite that sine to the 4th, right?
I have a question.
Yes,
So can you do like sine square, the whole thing squared then?
that's exactly what you want to do. So remember, the Pythagorean identities tells us the relationship between sine squared and cosine squared, right? This does not extend into any power. Sorry. It does not extend to any power. No, okay? It's only squares that formula works with. So we don't have sine squared. We have sine to the fourth. So you first have to rewrite that as sine squared x squared. That's sine to the fourth, right? And now you can replace the sine squared in the parentheses with 1 minus cosine squared x, then that squared. And now you make your substitution. U is cosine x, du is negative sine x dx. I'm off by a sign. So I just multiply both sides by -1. And then I rewrite the integral. Negative comes out, integral 1 minus u squared squared du. That's just a little bit different than the previous problem, isn't it? Just a little bit different. We had that additional, we have this additional squared here. Now that does have an impact, doesn't it? It has an impact right now at this step right here. We have to find the antiderivative of that. And you cannot do them one by one because it's being squared, right? So what do you think I'm gonna do?
FOIL.
Yeah, just square it. Okay, so square that. That would give you 1 minus 2u squared plus u to the fourth du. So I just did that on the side, like scratch work. I did it in my head, but I just FOIL. And then put those together, combine like terms, and I got those 3 terms. Now I can do each one of those individually. So minus, okay, antiderivative of that is u, minus 2/3 u cubed, plus 1/5 u to the 5th, all of that plus c. And then I'd replace all the u's with cosine. I went through that one a little faster than the last one. I hope you all understand the difference is really that 2 right there. That's that part in green. Okay, so sine to an odd power, we've got that kind of, yeah, right. You know, we get the basic idea. How about if we have this next problem?
Well, okay, I had a question.
Yep.
So what if it was like a sine to the 7th power x, and you pull out a sine, and you have sine to the 6th power? How would you divide that up into? Would you just do 1 minus cosine squared x, and then what would be the exponent outside? Would it just be 4 to compensate into the cosine to the 6th power?
Yeah, I would do sine to the 6th and rewrite that as sine squared cubed. Because 2 times 3 would give me my 6, right?
Okay.
And then that would give you a 1 minus cosine squared x cubed sine x dx. And then you do your u substitution, you're going to get a negative, you can get a 1 minus u squared cubed du. And then unfortunately for you, you've got to expand that. You got to do 1 minus u squared times 1 minus u squared times 1 minus u squared. Expand it all out, collect like terms. It's going to be messy algebra, but it's doable. And then you just integrate each one term by term.
Okay.
Good?
Yes. Thank
Okay.
you.
Yep. All right, so let's take a look at this one. Whoa. All right, so let's go back through the procedures here. Do we have sine? Okay, let's go back to the beginning. If you have cosine, right, that's the first thing. If you have cosine to the n with n being odd, do we have a cosine to the n with n being odd?
Yes.
We do, Right now, we also have a sine in here, don't we? But the first step says to look for cosines to odd powers, which we have. So what are we going to do in this case? If we have a cosine to the odd power, we're going to use a Pythagorean identity again. And this time we're going to factor out a single factor of cosine. So we're going to peel a cosine out now. And if we peel a cosine out, that means that we're going to be left with a cosine to an even power, aren't we?
Yeah.
Because we're peeling one of the cosines out. So I hope everyone sees that this part, the part that we're peeling off, that's always going to be our du. That's always going to be, whatever our u is, that's always its derivative. We might be off by a constant. All right, once we peel that out, we're going to rewrite the power of cosine using the Pythagorean identity, but this time solving for cosine squared. So we're going to be using our Pythagorean identity, but solving for cosine squared. So cosine squared x equals 1 minus sine squared x. I'm going to go ahead and do that to rewrite this. But that's cosine to the fourth. So I've got to do cosine squared squared, right? I've got to make this cosine squared x squared. So now I have this integral sine squared x in parentheses. What goes in the parentheses?
Cosine square.
Cosine squared, which I'm going to replace with
1 minus sine
Cos-
squared x.
1 minus sine squared x. But all that's still being squared, right? Don't forget you have this squared there. And then cosine x dx. Now for this method, we're supposed to make a substitution, but instead of u being cosine x like it was in the previous, it's now u is sine x. And the derivative of that will be cosine x dx. So there's my cosine x dx, right? That matches. All my sines get replaced with u's. What now?
Distribute.
Yep,
Expand and then
expand all that
distribute.
out, and then distribute a u squared. So one more step. And then we should be able to get the antiderivative of that, right? 1/3 u cubed minus 2/5 u to the 5th plus 1/7 u to the 7th plus c. And the last step I'm not going to do, but I've just replaced all those u's with what?
Sine x.
Sine.
Yep. So what you normally get here, whenever you have this sine to an odd power or cosine to an odd power, you usually wind up with some sort of polynomial. And that polynomial, you can just do term by term, just power rule on each one.
So would it be worth it to invest into memorizing Pascal's triangle?
I mean, I think it's great to know it, but I can't see us ever having to expand anything more than like something cubed.
Okay.
Yeah. And if we ever have some time, I can go through Pascal's triangle for everyone, if people haven't seen it. Okay, let's do, I have enough time for maybe one more at least. Cosine to the fourth beta t. Oof. Cosine to the fourth beta t. You know what? Let's do cosine squared of beta t first. Let's do that. This is a trig integral, right? It's an integral, it has a trig function in it. That's all that's in it. And so I'm going to go over here and I'm going to read through this. Do we have cosine to an odd power?
No.
No.
Is it 7? No,
No, it's 2.
it's 2.
Do we have sine to an odd power? No, we don't even have sine. Okay, the third thing here. If you have sine to the n or cosine to the n, no matter what, either sine or cosine with an even power. Do we have an even power on cosine?
Yes.
Yes. Then we're going to use one of these two half-angle identities. It just depends on what you have. Here we have cosine squared. So we're going to use the one that has cosine in it. And we're going to rewrite, we're just going to rewrite this using this formula. Okay, so I'm going to use the fact that, I'll write the formula down over here. Cosine squared t equals 1/2 of 1 plus cosine of 2x. That's the formula. I think I said t, I meant to say x. There's our formula. So let's just rewrite the integral. This is equal to, so I'm not peeling anything off. Do y'all see that? I'm not like peeling off a factor or anything. I'm just rewriting it. So this should be a 1/2 parenthesis 1 plus cosine of what?
2 beta t.
Yeah, you just, all you're doing is you're doubling what's in there. Whatever's inside, whatever's the argument of the trig function, you just double it. So that's going to become 2 beta t dt. I'm going to take the 1/2 out because I really don't need it in there. And now do you see that I can just do those individually, one by one? Just do the antiderivative of 1 and the antiderivative cosine 2 beta t. And I'll have a 1/2 out front. So the antiderivative of 1 would give me
T.
U.
t, because my variable is t, right? Okay, antiderivative of cosine of 2 beta t. Be real careful here.
2 sine 1 over bt.
Sine. Okay, so the beta, the
1
2
over 2 beta.
is the constant in front, right?
Oh, okay. Yes. 1 over.
So
2
1
beta.
over, so I'm gonna go plus 1 over 2 beta sine of 2 beta t. And then plus c. So that's using what we've learned already about antiderivative of sine and cosine, that if you have a number in front, a coefficient in front of the variable, you're going to scale by it. You're always going to do a little scaling on it. Okay, so that's it. We could distribute the half through, but I'm just going to leave it.
I have a question.
Yes.
Do we not put the t in the denominator for the 2
No.
beta?
You do not. It's just the coefficient.
Okay.
Yeah, because remember, the idea here is that if you took the derivative of this, the derivative of that in green would be cosine of 2 beta t times 2 beta, because the derivative of 2 beta t is 2 beta. And then you need to get rid of the 2 beta, so you scale by 1 over 2 beta. So the t does not come along. All right. That wasn't so bad, was it? Would you agree? I just used the formula, power reduce, we're done.
Yeah, this one is easy.
All right, but that's not the one that was in the examples. Do y'all see that that's not the one? The one that was in the examples was cosine to the 4th of beta t.
So we do the same thing, is just like whole squared then.
Yeah, so the problem here is that we can't use that formula because the formula has squared. We have to the 4th power. So we have to first rewrite this as cosine squared of beta t, but then that quantity squared. And that initially may not seem like it makes much of a difference, but it's going to make a huge difference. Huge. So now what I do is I go integral, and now I'm going to rewrite this in here using the half angle identity, just like we did before. So that's going to be replaced with a 1/2, and then in parentheses 1 plus cosine of 2 beta t. So there's the formula. But then all of that is being squared. Okay, so everything in yellow, right, the cosine squared beta t got replaced with the 1/2 1 plus cosine 2 beta t. But now we've got to square that damn thing, right? And that's not so easy. So we have multiplication, so I can square each one of these. So what's the way I'm going to write this? The 1/2 squared is 1/4. I'm going to bring it out of the integral. And that'll leave me the 1 plus cosine of 2 beta t. But that whole thing still needs to be squared. I haven't actually squared it yet. So all I did on this step was squared the 1/2, brought it as 1/4, and just wrote the squared on top of this. And now I have to square it. All right, let's do the squaring on that. 1 plus a cosine 2 beta t plus another cosine 2 beta t. So 2 cosines of 2 beta t. Can someone tell me what the last one is? Multiplying the last ones together?
Cosine square 2 beta t.
Plus cosine squared of 2 beta t. Good. Back to the integral. This becomes 1 plus 2 cosine of 2 beta t plus cosine squared of 2 beta t dt. Well, let's see which of these we can do. Can you find the antiderivative of 1?
T.
Yeah, that's just t. Can you find the antiderivative of 2 cosine of 2 beta t?
Yes, 1 over, so cosine, the 2 cancels.
Yeah,
So
you're going to have that 1 over a thing, right? So we can do it though, right? Like whatever it is, we can do it. Yes? Okay, can you do this one though?
Yes, we can use that, the formula before, the Pythagorean identity, I believe.
So we basically, you're telling me that we now have to do the antiderivative of cosine to an even power? Again?
Yes, I
We
think
already
so.
did that, no?
That's exactly what we, yeah, so that's actually the problem that we did right before this. So aren't we going to have to use that half angle identity again just for that part of the problem? Now I said it's exactly, it is not exactly because we actually have a 2 beta t in here. So let me just take this to the next step, okay? This is going to be equal to 1/4. How do I want to do this? 1/4, and then the antiderivative of 1, which is t, plus, let's see, the antiderivative cosine is sine, but then I have to scale by 1 over 2 beta, but I already had a 2 out there. So this would just be 1 over beta sine of 2 beta t. So I'm really trusting that you can get that 1 over beta out front using the formula. But then I still have to do plus the integral of cosine squared of 2 beta t dt. And I think to do that, I'm going to just do it right over here. So it's almost like we have to start this whole process over again, right? We have cosine to an even power. If we have cosine to an even power, we're going to use the formula and rewrite that as 1/2. And then what goes in here?
1 plus cosine 4 beta t.
Good. Cosine of 4 beta t. It's 4 beta t because we're doubling 2 beta t. And when you multiply 2 beta t times 2, you get 4 beta t. So it's real important that you understand that that 2 beta t gets doubled in the formula. All right, now that's equal to, let's see, 1/2. Can we find the antiderivative of each of those?
Yeah.
Antiderivative 1 is going to be t. The antiderivative cosine of 4 beta t is 1/4 beta sine of 4 beta t, which is 1/2 of t plus an 1/8 beta sine of 4 beta t.
So you just multiplied the 1/2 across?
I just passed it through. Could have probably written it all down already by now, but okay, so we were here. Oh, I forgot to close my brackets up there. So we were here. We had to go do this integral on the side. We did, and then we brought that answer back in and plugged it in right here. Now we still have to distribute through with the 1/4. But once we distribute the 1/4, we're there. Wow, so making that a cosine to the 4th really kind of added a whole other level of work there, wasn't it?
Yeah.
Can you imagine what cosine to the 6th would be? Cosine to the 6th is what I consider to be a torture problem. That is you wind up having to do this thing twice. So
are you going to give such type of problems like cosine to the 4 on the test?
cosine to the 4 on the test is fair game. Cosine to the 6 would just be mean. But I'm going to look in the book here to see in 6.2 if they actually have cosine to the 6th or not. They have cosine to the 4. Oh, they do have cosine to the 6th. It's number 10. Oh, and I should point out, I think I said this before, but I just want to be clear. When you're doing your homework, if you see numbers, like this is number 10. I think this is number 10. Oh, 0 to pi. Okay, so if you see this on your homework, you are to ignore this completely and just go find the antiderivative. Forget those numbers on the top and bottom. We haven't talked about that yet. So the reason that's important is because when you go, if you're looking at the solution manual in the back of the book or something online, solution manual wise, you're going to get a number as an answer where you're actually just supposed to get the derivative. I mean, antiderivative. That's all I want you to do right now. So watching my videos, I think would be, you'll be better off that way. Okay, so what should you do for homework? Of course, finish 6.1. Okay, make sure you got 6.1, done. And then for 6.2, the first 10 problems are within grasp. Actually, probably the first 16 problems out of the section are within grasp. And when I say the first 16, I mean like if you were to just do the odds, that would be okay. Like 1, 3, 5, 7, go through 15. But don't try and do anything after that because we haven't talked about that yet. Any questions on that?
So for the question on the homework, how many are we supposed to do?
I would suggest that you look at the problems numbers 1 through 16 on section 6.2, 1 through
Okay.
16. Now, if you want to cut that down, just do the odd ones. But if you want to get really good with this, I suggest you just try and do them all.
Like you mentioned in the syllabus.
Yeah, the more you do, the better off you're going to be. Okay, well, I know that it's been a long week. We got our first test out of the way, and don't if you didn't do as well as you wanted to, I mean, don't beat yourself up. Like I said, make sure you make adjustments. I think one of the most frustrating things is that while I'm interacting with you all here, that a lot of times I'm getting correct responses from people, and then the test doesn't seem to reflect that same thing. So I know that part of this is probably just testing itself is something that you might be struggling with. And there's ways to get better at that. There's ways to get used to, train yourself for a testing environment. So get with me and I can help you out, see what we can do. All right. Anything else? Good. Okay, you all have a good weekend. I will see you on Tuesday, and we'll get through the
All
rest
right,
of
sir.
the session.
Have a nice weekend.
All
sir.
right.
Have a nice
All right,
weekend, sir.
take care.
Thank
everyone.
you. Take
I have
care.
Very much.
I have a quick question for you real fast.
Yep.
So on our